Hi, Baji. Hi, Baji. Hi, Baji. Hi, Baji. Baji, it's time for a little lesson. Mama's gonna make a tea. Mama's gonna make a little tea, and then Mama's gonna teach some physics, okay? Hello, everybody. If you're joining, please do like, share, subscribe, and let's get this going. I hope you've joined, and I hope you're here to learn, and I hope that I see many of you tonight, old and new. Please do subscribe. Let me get this pulled up on my other phone. Hi. Oh, Baji. Oh, Baji. Baji's so cute. बाहों में आ जाओ, सपनों में खो जाओ, तुम दिल की धड़कन में. Construction, how are you? Hello, my love. Please do like, share, subscribe. I think you've been here before. If so, welcome back. Hello. Yes, it has been a while. Shut up, Jeremy. Don't lie on public television. Construction, hello. Jeremy King, hello. Welcome back. I'm good. I had surgery, I recovered, I went back to the gym, all of this stuff. Please do like, share, subscribe, guys. I think I've seen you since my surgery, though. I was sitting on the sofa, on the couch over there. But now I'm back on the kitchen table. I'm never signing the divorce papers. Jeremy! All right, let me make my tea. Can you guys do the things where you hit the buttons, like, share, subscribe, do some emojis, help me out here. Divorce papers. Jeremy. Here's some tea that I will be drinking with you guys, and then we will be talking about physics, astronomy, astrophysics, and cosmology as usual. I just got back from the gym a little while ago, and then I did chores. So, not in the best outfit right now, but I think it'll have to do. Hello, everybody. Where's my mods? Is, hi Ryan, is Ben here? Hi Key, Ben, how are you? Where are you? You fired them all? Well, can we get 10 likes? Doctors tomorrow just travel back to Washington. Hi, construction. Sorry, guys. Give me one moment. I'm still collecting myself here. I hope you can see Baji. He's ready. Ready for class. I'm just chilling, waiting to fall asleep. Of course. This is the sleep medicine channel. Of course, entertainment purposes only. This is not a healthcare channel. But it is used by a lot of people to fall asleep. Hi, Jay Franks. Oh my gosh. Oh my gosh. I'm in outer space. God, I think I am. This tea powder is like super rich. But it's actually not bad. Post-workout little tea and milk. Hi, J. Franks. Kitty cat is right there on the tree. Do you see Baji? Baji. He looked up. Oh, I never came to Italy. I'm not in the shower, I'm here. Shut up, Jeremy. Do a super chat. I'm doing dishes. I'm about to teach you something. Okay. I am here. Are you guys ready to learn? And how come I only have this little number of likes? Please, guys, can you up that? Okay. All right. Let me sit down. Ugh. I didn't do my hair. It's a little messed up. But you know what? This is gonna have to do for tonight. We are here. Cat Mom. Thank you so much for liking the live. Let me raise my eyebrows. Ladies and gents, we are back. I had to be gone. I had to be away from you a little bit, but I have been around. I am making other videos, clips, shorts. Please do give us a like, share, and subscribe when you come across those things. If you haven't subscribed, please make sure you do that so we can see you in ongoing, upcoming lives. So, are you ready to learn tonight? I'm thinking of teaching you guys the redshift equation, but let's see. What are we in the mood for as far as physics and astronomy? Or should we do... We talked about giant stars. We talked about black holes quite a bit. Oh, you know what? We could talk about neutron stars. So I had a surgery, then I recovered. Doing better now with the thanks to the universe, and I've been a little busy with all kinds of things, like my other projects. But I do hope that I will see you regularly for these lives. Sorry about that. This is a live where we cover physics, astronomy, cosmology. This says Cat Mom. Oh, that's right. In Italy, 6:30 a.m. Hi, Rajkumar. Hi, Jeremy. Hi, Construction. Hi, Chris. Time travel. Okay. We can talk about time travel. So we've talked about girl dad cooking up deliciousness. Oh, thank you so much. How are you? Let me look at the top fans really quickly. So the number one right now is Construction. Thank you so much. Number two is Jay Franks, I believe, from Italy. I'm sorry I haven't been to Italy this year yet. I mean, as soon as I make more money, maybe I will do that. Number three, Jeremy King. Number four, Chris. Number five, Rajkumar. Number six, Girl Dad. Number seven, Ryan. Number eight, Big Frank. Oh my goodness, thank you, Kelly. Hi, Kelly Anderson. Kelly Anderson has sent a treat. Goodness gracious me, thank you so much. I have 3 children who are all feline. This is a T. Hi, handsome, huge, whatever. My day was okay. Hello, Win3, are you okay? Yes. Oh, ha, luck, Arushi. Hi, Arushi. Italy may be cheap, but I do have to get there on a flight. Hello from Cleveland. Hi, Big Frank. Okay, guys. So, we talk about all kinds of topics here. We've talked about black holes a lot. We've actually also talked about time travel. We said how in time travel, it's actually pretty customary, pretty normal for microscopic things to do time travel. Like particles are doing it all the time, but macroscopically it can be difficult. So that too is a topic that we have touched upon, indeed. Let me make sure all the settings are good for this live. 2 cats. If you could have one superpower, what would it be? I have enough already. If you're new here, please do like and subscribe. I have a few superpowers already, I think. I'm good. Actually, I would make sure that I would try to go without sleep and without food every day. I think it's most inefficient. Are you under the impression that the particles move forward? Yes. Mm-hmm. Correct. Yes, indeed. Can I elaborate? Yes. Are you familiar with Feynman diagrams? Is it true that cat odors? That's an interesting statement. So once again, please, I need to... Hello. Hello, 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 hello. Do I believe in aliens? I believe in researching for exoplanets, which would be one way to look for aliens. Because, you know, to have life in other places, we must have planets to support such life. Oh, really? Was the new Spider-Man movie good? Thank you, Big Frank. There are studies based on... Oh, I didn't know that. That's very interesting. I'd be very interested in these studies. Let me know. So, I'm trying to remember which book we referenced, which was sort of an easy way to understand time travel. But we have certainly talked about it. I will touch upon it tonight since you asked about it. For a second there, I thought you were an Indian girl. Hello, Turkish. Hello, 710. Hello, Nee. I do have a PhD in physics. I'm from Mexico. Okay. Figure out how to go back in time, let me know. Well, it's difficult for macroscopic objects like us to go back in time. That's difficult. But particles at, quantum scale is different from the classical scale. So I would say in the quantum scale of particles doing things, it's completely normal to go back in time. Happens all the time. But for extended objects and the classical scale, it's difficult. B is a certified mamacita. Well, thank you. Sorry I look a little crazy today with all my hair and everything. I didn't take my shower yet after gym and chores. Hopefully next time I will, and it'll be a little better. This is true. You can support actual human beings for the last time. Hello, Dune One. It's going well, thank you. Thank you so much, Dune One. Please do subscribe. Chris Cairn is saying this is the last decade of humans watching us stream. Going forward is likely to be AI agents and humanoids. Well, this is a human being right here. Thank you. Good night. Enjoy your talk. They're saying you're from Mexico because of your accent. I thought if two massive black holes orbit and have opposite rotations, they can phase shift a macro object backwards in time. Well, I would imagine such an environment to bend space-time, but I'm not sure about this backward time thing. I thought, okay, hi Barth. Schrodinger equation, by chance is your full name. The name is Oendri, just Oendri, no la. You like my hair, okay, thank you. I need to wash it, but thank you for the kindness. Hello, Hitch. Hi, human being. Hello. So, I'm not sure I follow about the two black holes. Black holes are pretty extreme. I would say, the most extreme sites of gravitation, very extreme gravitational field, bending space-time. But as far as I don't follow about the time travel. But I do want to clarify what I mean by... Hi, Vuri! How are you? I'm here. I'm here at the kitchen table, the kitchen counter, once again. I had made it to the sofa after my surgery, but now I'm back. First 50 Dates movie showed easier way to time travel. Hi, The Sid, how are you? Why do I look like the cosmic princess? Oh my goodness. That's a great title for today's live. Cosmic Princess. I love it. Okay. So I think I have done the thing where I do the thing. It's nighttime for me. I look like a gym model? Oh my god. Hi, because. Ah. That's right, cat mom. Okay. Have I done the other thing with the thing? Hello, Chantal. There's like a frame dragging effect caused by the limits of the photon trajectory in the... Hi, Finding. I think I returned that book to the library. The one... So, as far as quantum loops are concerned, if you've seen Feynman diagrams, actually, if I believe we've covered this on the lives previously already, book by Stephen Hawking, if you were here for that. And if not, you know, of course, all these live streams get uploaded and saved and everything, so you can go find it later on. But basically, in short, just to summarize it, Stephen Hawking had noted that microscopic particles and antiparticles, so an example would be the electron and the positron, for example. So these microscopic scale things, particles and antiparticles, can mathematically behave as if they move backward in time during quantum fluctuations. So it's pretty standard for particles and antiparticles to do that. Okay, so of course we're talking about the quantum level, but we do know about that. And then there's also you know, sometimes particles can move at pretty high speeds, and as we know, you know, with special theory of relativity and general theory of relativity, space-time is relative. So we've got that as well. So if you want to look at it in that way, so there's a couple different ways of looking at this. I mentioned about the particle antiparticle quantum loops. That's one way. And then there's also time travel into the future happens naturally for fast moving particles when subatomic particles accelerate. So, you know, kind of like time travel. When subatomic particles accelerate close to the speed of light, such as inside the Large Hadron Collider, time slows down for them due to relativistic time dilation. So there is time dilation, which would be a thing as well. As a result, they live significantly longer than stationary particles, acting as real-life time travelers to the future. Hello, Upland. So there is that. So you have to you have to be like, what do you mean? Time is relative, as we know, according to relativity. And so note how this is still kind of talking about microscopic things, though. Particles are very small. So those types of things often, I mean, even the astrophysical high energy neutrinos, right? So you don't have to always get these particles to be something in the Large Hadron Collider, but it could literally be a naturally highly accelerated particle coming from some exotic site in the universe, some other galaxy or something. And those particles can also travel really fast, close to the speed of light, not the speed of light, because, you know, if a particle has mass, it cannot travel at the speed of light, but maybe close. And at that point, you do have to consider relativity. Yes, neutrinos, exactly. We've talked a lot about that as well here on the channel. And then they would, they would experience time dilation. And then there's also the quantum loops. Stephen Hawking proposed the chronology protection conjecture, suggesting that physical laws prevent macroscopic objects and humans from ever traveling backward into the past to avoid paradoxes. So according to him, at least from that book, when we were covering the book, he's saying that time travel is not possible for macroscopic objects like you and I. Okay, so if you read The Brief History of Time, which we covered, because, you know, on this channel we talk about these topics and we often reference books that are like well-known books or textbooks, actually. And so A Brief History of Time certainly covers this. We talked about how, so remember, if you were here, we even talked about the concept of time and in which ways time going forward, and how, you know, there's a couple different ways. There was like psychological time that he talked about. There is thermodynamic time. So the way, the direction of time that allows for entropy to increase is the forward direction of time, all that stuff. Hopefully that's ringing a bell if you were here. And if you go back to that live, it should be posted under the live tab of the channel. Then certainly we will, you'll see us talking about this in a lot of detail. So yes, time travel for macroscopic objects, according to him, is not possible. But if you find a way, do let me know, okay? Time travel for bigger objects, like macroscopic things, you and I, kind of hard, okay? Thank you so much, Upland77, for this super chat. Oh my goodness, thank you so much. Wow. Upland77 says, I'm new here. Thank you for sharing your knowledge. Oh my goodness. Thank you. NHO Noj. I just have to make sure it's not a... Okay. Hello, Noj. Nancy Grace totally disagrees. Okay. Whatever that is, I'm not sure. What if we turn into particles? Well, then it's possible. There's Baji behind me. Here. He's sleeping and listening and getting wiser on physics. Have you listened to... Hi, Noah. I'm not sure what that is, and I probably haven't. Hello. So yeah, that was the answer. That was the little nugget on time travel for you guys. I wanted to reiterate that it is possible for particles. It's quite standard for particles. So don't think of time travel as this like big exotic thing. Depending on the scale, for particles and quantum scale, it is very much an everyday thing, such as with those quantum loops and particle antiparticle types of interactions and quantum fluctuations. It's happening all the time. And then also the fast moving particles, which could have time dilation because of relativity. I don't know if I like a robot voice. Does our brain signal travel faster than speed of... Well, I mean, if I get it, I don't know much about life science, but brain signal would mean like some kind of neurochemical interacting or getting received or something. So it's like chemistry, and chemistry is like electrons, and electrons have a mass, and so there is no way that it could travel faster than the speed of light. It would have to be slower than the speed of light. Although, if you know any better, then let me know. Thank you, Noah. He is really cute. Thank you so much. Hi, Cyclone. How are you doing? Morocco night ticket. We're up all night. Okay. Is that the song? Thank you so much. So yeah, I would imagine biochemistry, chemistry, electrons, cannot travel at the speed of light, okay? Anything with mass cannot travel at the speed of light. Can light become gay and merry? I believe it already has. Light has so many colors. And wavelengths and frequencies. Next question. Shall we do a little bit of reading on neutron stars? Did you subscribe? I'm still on iPhone 15. But congratulations to you. Thank you, Upland. Jingle bells, jingle bells. Did you know that I was like getting some email today about like the holiday season? It's August. I don't know why I'm being asked to think about the holiday season. Subscribe Thank you, Noah. Please do subscribe. I look cute? Oh, well, you're kind. This is my messy hair after the gym and chores. And I didn't even take a shower yet. Although I took a shower at the gym, but my shower to get my hair ready, I haven't done today. For you guys. Tomorrow, maybe. On the holiday season, yeah. Thank you. Noah said, I love your voice. Thank you so much. I know, I think I got like a survey. I do those little Google surveys sometimes, like when I'm in the bathroom or on the bus or something. And it's asking about like shopping. And I'm like, well, first of all, I don't shop. I don't believe in shopping unless it's on a deal. Forget time travel. I don't even believe in shopping. And second of all, don't tell me about Christmas. Christmas better be not here. Holiday season starting. I mean, it's August. What holiday? Labor Day? I don't even want to think about Labor Day at this time. How many different dimensions are to be believed? Oh, that's a great question. Oh, man. I love when somebody asks about string theory. What workout today? Do you have YouTube on your computer? I do. I have the live going on in my computer to be able to see it better. Do you take creatine and protein powder? I do not, as far as I know. Shopping is relative. Shopping dilation is dangerous. I love it. Or on your phone, go on search and okay. May 1st. No, Labor Day is in September. End of May is Memorial Day. So somebody asked, we'll come to the dimensions thing. So today workout, I mean, I just did swimming. I did not lift weights. I did swimming and then I walked. Like I did my swimming, then I took the bus and then I walked. LA. I'm in Boston. Hi Lugai. Hi Sada. Hi Sadananda. Hi Vuri. Hello Upland. Hello Construction. Rajkumar. Hello Shaba. Hello John. Okay, so John SCZ asked about how many different dimensions are to be believed. And I do love that question a lot. Where am I from? Well, I'm in Boston, but the rest, you can guess. Hi, Anderson. Hi, Yatin Kumar Sahu. I meant to say when they say, are Boston donuts same? Are Boston donuts same as black holes? I don't know. Maybe. Okay. I don't know. The Q test. Are you an MIT professor? Nope. Okay. Let's talk about string theory and M theory really quickly. Since somebody asked about the dimension question, I'm checking on my. So. First of all, there's two things. There is normal string theory and then there's M theory. Oh, are you in the 3rd grade? Well, you should subscribe, honey. Subscribe and tell all your friends to subscribe. Do I have kids? Well, you are the kid. What is light as in speed of light? Light has all color. Raphael from Switzerland. Right? Salma Hayek's daughter. Yes, that's correct. Where my hair is done by the chlorine. Actually, not really. I put a swim cap on. Okay, so string theory has 6 extra dimensions. M theory has 8 extra dimensions. Okay, so let's talk about it. Let's talk about it really quickly. So as you know, in our physical world, the way we experience reality, we have 3 spatial dimensions and 1 time dimension. So, 3 space plus 1 time dimension. And general theory of relativity, which is Einstein's theory for gravitation, basically puts the math together for these 4 dimensions, the 3 space and 1 time. Because Einstein was really a person who believed in keeping things real. So he did not, he didn't create a theory which has any extra dimensions and such. So in that sense, if you are wondering, like what's the tried and tested number of dimensions, we would have to say it's just the 3 space and 1 time dimension, because Einstein's general theory of relativity is very much successful so far to a large extent. I'm not saying it's successful at everything, but it is to a large extent good. So whatever he did, his work on describing gravitation, utilizing the 3 space and 1 time dimension, is what we've got. But then when you come to string theory and trying to kind of merge classical, which is general relativity, with quantum mechanics and all that stuff, and try to get particles explained and all that, then you have to add these extra dimensions that we talked about. So depending on which version of string theory, you've got either the just the regular superstring theory, and then you've got M theory. So the fundamental object in superstring theory is is the one-dimensional vibrating strings, and in M theory, it is one-dimensional strings and 2D plus membranes. So sometimes people may call them branes, just BRANES. And then the total dimensions in string theory is going to be 10 dimensions, because you've got the 9 spatial dimensions and the 1 time dimension. So total 10 dimensions in string theory. And then M theory has 11 dimensions, because you've got total 10 dimensions of spatial and 1 time dimension. Yes. So then it's saying with string theory, there's 5 competing mathematical variations. There can be some variations of how you do this math. And in M theory, there's a single master theory unifying all 5 variations. So that is the contribution of Edward Witten. So if you are into this kind of thing, then you should look him up. I'm sure you probably already know him. How do women switch? Switch what? Hi, Ligmag. Hi, Ahmed. Salma Hayek is from Syrian ancestor. Well, apparently she's my mother. So there is that. I'm so happy that you remember me still. Of course I do, Raphael. I remember all my old true friends on the channel. Thank you for your support. Switzerland. Yes, that is me. What up? I've been seeing you in a very, very long time. Thank you. Well, if you see my shorts, please do leave a comment. Helps me out. Can you teach about quark theory? Well, quarks are a part of quantum, mechanics and particle physics, so we can certainly talk about that. Thank you for subscribing, Logai. Are you from New Delhi? No, I'm from Kolkata. Hello, De Silva. Was Einstein Indian? No, but he did come to India. And there's a famous picture of him with Rabindranath Tagore. Hello, Surendra. Do I know Hindi? Yes. Which theory does sliders? I'm not sure what that is. Hello, JC2004. I got my new phone because my old phone. Good job, Raphael. Hi, JX4GG. My name is in my username, so go ahead. Actually, somebody asked about my Instagram ID. It's the same ID username as my username here, so go ahead and follow there. Instagram is small, but you know, feel free to follow. You know that my birthday is coming up soon. I'm turning 27. Oh, that's right. Happy birthday. Early one to you. My hair looks beautiful and clean. Thank you. Well, I try. I did take a shower, but not like my full shower. This girl is extremely intelligent. Oh, well, thank you so much, Matto Rents. Matt Torrance. Hello, Matt Torrance. Am I into science? Indeed, I am. Matt is saying Calcutta like Mother Teresa. Yes. I met her, actually. Scientific girls scare me. Hello, I'm saying. Do you think stem cells can fight string theory? I don't know stem cells enough to answer that. I'm very much in awe of people that can talk about stem cells, though. I wish I knew more more biology, life science, all that stuff is something I must have, what's the word? Neglected because of going to school for physics. I fear I have neglected stem cells. But I have some really, I have maybe one at least, really smart person I can talk to about that. Because I'm in Boston, lots of people work on such things. Barth is saying she's from Spain. Maybe I am, I don't know. Everybody is from, pretty much everyone is, I think, from the same place. How do I talk to girls? You're doing it right now. Hello, future John. Love you so much, Raphael. God allowed science, which science tries to overcome. Do I use LinkedIn? Yes. I think my LinkedIn is the same username as well. I think my username is like the same everywhere. Thank you so much. Can we get 20 likes? I got braces today in the dentist. What's your Indian name? The one that's in my username, the first part of it, ON3. I believe there is at least 3 dimensions. There is 4 dimensions, including time. Hello, Sadananda. Hello, Nolan. Maxwell. I love that name, Maxwell. Maxwell was a great scientist. NASA ON3. The toughest PhD to do is physics. Thank you. Priya was so hot on. I don't know who that is. Hello, Matt. Hi, Upland. I did meet her when I was a little girl. My girlfriend left me because of my Lincoln Park obsession, but in the end, it doesn't even matter. Hello, Demi Rosak. Hello, Demi. Your girlfriend left you. Okay. You look exactly like Priyanka Chopra. I really don't think so, but thanks, I guess. She's from Mexico and Spain. I don't know if Priyanka Chopra is from Mexico, but okay. Don't think so. Please do not donate your hair for science. I've donated my hair a couple times for wigs. You couldn't have neglected stem cells. Thank you. She's French. Hello. Hi, Rodriguez. Hello, beautiful, smart lady. Oh, thank you. Hi, Noah. She's Jamaican and Jewish. I see your comments. Thank you so much, everybody, for being here. Let me get back to the questions. So, string theory basically replaces zero-dimensional particles with one-dimensional vibrating strings. So, the fundamental unit thing there is a string. The way a string vibrates determines its mass and charge. So, it's basically having this universal theory of everything way of describing particles and incorporating general relativity. So because general relativity kind of lays the foundation for the Riemannian geometry and the way of putting together the math with 4 dimensions, including time and the 3 space dimensions, now you're just extending that to include 6 more dimensions to give us string theory, and 7 more dimensions to give us M theory. So the string theory version, which actually it's called superstring theory, by the way, you need supersymmetry. If you, again, this live or much more about this topic is already posted in the past under the live tab of my channel. We went into a whole thing about supersymmetry a while ago and how you need that. And supersymmetric string theory is really what we talk about at this point, because string theory, I believe, without supersymmetry does not actually work, okay? So anyways, string theory is we're replacing particles with, instead of thinking about particles as sort of these separate entities that each kind of come with their own properties and all that stuff, we're kind of generalizing and trying to have a basic theory that would describe all particles and mathematically describe all particles. Okay, so it's a highly mathematical and geometric kind of theory. So instead of being sort of rooted in physical, intuitive what's the word? It's not super physical or intuitive. It's mostly geometric. It's mostly something that people have worked out geometrically and got this theory going. Okay, so you've got these vibrating strings. The way a string vibrates determines its mass and charge. So basically all these properties in quantum mechanics, like mass, charge, spin, color, right? Those are some of the properties. Quantum properties of particles were already being discovered at the time when people were trying to understand if there is a more universal theory, okay? So like a theory of everything. So what happens then is that once you try to have a theory of everything, you actually have to then describe and properly explain all of the properties and all of the particles that were already known. You can't just have a theory of everything which does not cover everything, right? So sometimes this is called unification theory. So theory of grand unification theory sometimes, right? These are the sort of same like different names of the same thing. So in the ground unification theory, you're trying to have a universal fundamental way of describing what's known that merges together our knowledge of gravitation as well as particle physics. And so particles, which were constantly being discovered in the 20th century, I mean, even something like you know, the atom that has a nucleus has protons, neutrons, all of these things and details were coming out, and quantum mechanics made sort of leaps and bounds progress in the 20th century and provoked people like Einstein, for example, to think about, like, well, how do you kind of bring it all together to be explained by something basic instead of having to worry about just a jungle of particles and their properties, which is kind of what the standard model of particle physics is. What is an underlying basic theory that can describe it all? And, he died trying to get that going. Basically, it was very difficult. And then, after a while, people picked back up on certain early work by Kaluza Klein, and then, string theory started getting advanced. And so that's the context. Okay, so these people are not being like crazy. They're starting from somewhere, and they have a goal in mind, which is to be able to explain and postulate, like put particle physics together with a basic thing. So instead of thinking about these particles and properties as these, various different things, they're considering the strings, the vibrating strings, and the various, modes of vibration, if you will, and the way the string will vibrate will basically, for example, give you the mass and charge. Similar to how different vibrations on a violin string create different musical notes. So that's just an analogy. Okay, so because string theory is a highly geometric, mathematically heavy topic, it's kind of difficult to intuitively talk about it or explain it unless you give these types of analogies. So that's what we're doing. Now, then there's also M theory, and for this, please do check out Edward Witten, for example. Edward Witten, physicist, person, people know about him. M theory unifies 5 different versions of string theory. So because, string theory, people can also kind of disagree between themselves probably. That's something that physicists are very good at, is disagreeing with each other. So M theory, I guess, takes all that into account and adds an 11th dimension and introduces 2-dimensional membranes or branes alongside strings. So, I mean, basically, if you've added 6 extra dimensions, spatial dimensions, then why not one more? I will mention now. So the question, all of this that I'm talking about is coming from the question of somebody asking about dimensions. And so now let's talk about some of the problems here. Even though this is an elegant theory, string theory and M theory, these are good, elegant theories, but the problem is that they cannot be experimentally verified. These extra dimensions in spatial dimensions that these theories require, like the 6 extra dimensions in superstring theory, that is not experimentally verifiable because these dimensions are extremely tiny. So we would have to probe very small scales, super duper quantum tiny scales, in order to be able to prove out that these dimensions are real. And indeed, we'd have to go back to sort of like these early universe, Big Bang type of, environment or conditions in order to really get there. So in today's day and age, in today's version of the universe, it's very difficult to find and prove out that these extra dimensions exist. So you may or may not believe in them. And that's fine, because in today's world, in today's universe, we cannot really see them. At least not to my knowledge. We haven't been able to see them, okay? So as far as that goes, string theory remains a theory, a candidate theory for the grand unification efforts. We can't really call it a super real thing because you cannot verify it, okay? But depends on who you ask. Either you can just say, yep, we have the 3 spatial dimensions and the 1-time dimension, which is what we experience, which is what Einstein wrote the general theory of relativity for, and you just call that a day. Or you could be a string theorist and then you have 9 spatial dimensions and 1-time dimension. And in M theory, you have 10 spatial dimensions and 1-time dimension. So depends on who you ask, you'll get these types of responses, okay? So I hope that I covered sort of what you asked. And we do have a lot more about this as well in the past lives under the live tab of the channel. So, and yeah, remember, we're trying to merge general relativity with quantum mechanics. We're trying to describe all 4 fundamental forces of nature, including gravitation, which is very difficult. They explain why we only see 4 dimensions by suggesting extra dimensions are curled up tightly at microscopic scales. So we only experience the 4, okay, including time. So if you want to just believe in the 4, I don't blame you. But at the same time, we can have an open mind. Somebody said that I lost them. Well, too bad and so sad. Hi, Amsang. Time can bend, yes or no? Time is relative, yes. Gravitation is the thing that's doing the bending. And so for different observers, time will be longer or shorter. And same for space. So space and time are relative. Basically, the way you're measuring time, the way you're measuring space, it depends on the observer and your gravitational environment, that's like space-time curvature. Because gravitation, remember, think of it as like it's Riemannian geometry versus the Euclidean geometry that we learn in school, okay? Let me real quick tell you about Riemannian geometry. That will be... So generally, the problem is in school, we talk about Euclidean geometry. Spaghetti paradox. I don't think so. I don't think I have. String theory makes me realize. Hi, Jax. Hi, Truth Hurts. Are you talking about spaghettification near a black hole? Guys, imagine you have a girlfriend like Oindri. Headache every day. This is why I don't date. Hi, Sean. Nobody likes me. Once the spaghetti has been in, okay. I like that question. Liberal, tears. What time is it? 2:30. I don't want to stay up too late, but your questions are really good tonight. Guys, I'm impressed. Your questions have been really good tonight. Thank you, guys. Please subscribe. Do you think the universe will quit expanding at some point and start to retract and all will become one again? So you're asking about the big crunch. Quit expanding at some point and start to retract. Hello, Surinder. You're very pretty. Well, thank you. Yes. So by the way, you should definitely find my string theory lives from before, because we absolutely did cover certain topics from a couple of different books, and you can read those books. I probably tagged those books. Go find my lives earlier from those. Just search like string theory on my site, on the YouTube channel. And thank you for your question, John S. ZZ. On LinkedIn, yeah, that's my name on LinkedIn. Yep, you should be able to find me. Give my regards to Salma. Oh God. It makes sense. Andrea B is PhD and expert in a bunch of things. Her resume is so big. Well, thank you. Thank you. I'm just a country boy. My boyfriend and I are watching from Florida. Hello. Hi, Mr. Drew. Okay. Hi, Javier. Thank you so much for all the support. I did watch Interstellar. Thank you, Avik. Okay, so we're going to talk about the expansion question. I like it. Liberal has asked about the expansion of the universe. What do I think of that? Hi, Justin. We're taking questions. I mean, my hair is a little wet, and the weather has probably done something. I used to have a girlfriend. Okay. Nobody likes intellect. But thank you. Your hair looks different. It's so thick and luscious. Oh, thank you. So let me real quick tell you about Riemannian geometry. So think about it this way. In school, like, I mean, at least in my school with high school and all that, we never really learned Riemannian geometry. We learned Euclidean geometry. So what is Euclidean space? It is flat and uniform everywhere. So flat is Euclidean. So like all the stuff that we learned, all those geometry rules, triangles and planes and quadrilaterals and 2 points and a straight line and all that stuff, that is Euclidean geometry and Euclidean rules. Okay? This is going to be very different from the geometry that we use in general relativity, which is Riemannian geometry. So, Riemannian geometry studies curved spaces by generalizing flat Euclidean rules using a smoothly varying inner product on tangent spaces called a metric tensor, allowing local measurement of lengths and angles while discarding global flatness. So instead of having flat space, we have curved space. So comparing, so Euclidean space, once again, flat and uniform everywhere. We can do our regular geometry that we learned in elementary school or whatever, high school or whatever. So this means space does not bend or change properties from point to point. So like the definition of a straight line, we all get it, right? Now, think about Riemannian geometry. It's going to be a little different. This is going to be a manifold. Riemannian manifold is going to be curved and variable, meaning the degree and direction of bending can change continuously across the space, across the manifold. So if you've got 3 space dimensions and 1 time dimension, that's a 4D geometry. And it's, you know, general relativity is saying that gravitation makes this space-time curve. So the perfect way, you know, the appropriate way to describe, what do you call this type of thing is Riemannian geometry, right? So that's exactly what Einstein did. He became a good student of geometry and especially Riemannian geometry, and he put GR in terms of Riemannian geometry because we've got 4 things now, 4D instead of the 3D, that we all know and love in Euclidean space. So another little example here is Euclidean space would be like something like what we learned in school, where parallel lines stay the same distance apart forever and they never meet. Riemannian manifold is somewhere parallel lines can converge or diverge, such as lines of longitude meeting at the poles on a sphere, just kind of like our Earth, right? The Earth is curved. Think of that as sort of like an analogy of Riemannian manifold. So the basic framework of this math that you need to describe GR is Riemannian geometry. So now imagine if you've got the general relativity set up for 3 spatial and 1 time dimension. So now if you extend that to include more spatial dimensions, then you will have superstring theory and M theory. Of course, there's more things too to consider and whatever, they do that. But pretty much GR is giving you a way of having more than 3 dimensions. So then you take that to like 10 dimensions or 11 dimensions, okay? So if you're ever wondering, like if you want to take, you know, GR in grad school or something like that, definitely a string theorist would be a great choice for teaching the class. And oftentimes, it is a string theorist that teaches a general relativity class. I'm checking on a project of mine. Okay, that's done. All right, guys, let's talk about expansion. So please do look up Riemannian geometry, okay? If you're interested in these types of things, GR and all that. Thank you guys for all your questions. Let me catch up with your comments here. Do you think Nicholas is correct? Which Nicholas? Nikola Tesla or someone else? Hi, Dodge. How are you doing? Hello, Ricardo. Oh, God. Hi, just in case. What's my favorite color? Pink and black. Okay, so now let's talk about expansion of the universe, like somebody asked. So I would say the long story short answer for, if there is going to be a big crunch is I don't know. But as far as I understand, there is no evidence of such. So we don't really see the universe's expansion slowing down. We see it accelerating. There are various cosmological models, and you can absolutely play with those parameters to see sort of which which universe comes out of what. But I believe the one that kind of agrees with our observation and all that stuff is the one that is expanding still, and that expansion is accelerating. The universe is expanding. So that's why people, so remember we talked about this, the ingredients of the universe: dark energy, dark matter, baryons, photons, neutrinos, those 5 things. And dark energy, dark matter, those are both research topics. Dark energy causes the expansion of the universe in an accelerated manner. And there are so many, well, I want to say at least a couple different really big collaborative efforts going on to further understand that. So one of them is called DESI, Dark Energy Spectroscopic Instrument. And the other one is Dark Energy Survey. There are 2, different methods. So we do want to have sort of complementary ways of understanding this universe, and picking up on like signals, measurements, things like that. The problem is that with some of these efforts, like as far as I understand the DESI experiment, which is Dark Energy Spectroscopic Instrument, I mean, I was at a conference. I still need to post the videos from that conference. But they don't have, I believe that they don't have enough measurements yet to say certain things fully confirmed, like. So we just have to wait, but they are working on it. Thank you. Please, can you subscribe? So it was 4 months ago. I'm sorry. Well, no, it was 2 months ago. I went to a conference 2 months ago and I still did not post the videos. I think I posted like a couple, but I need to post a lot more. I've been kind of too much going on. So the universe is expanding at this time. We are in an era of dominance by dark energy. And this expansion is accelerating over time. The Dark Energy Spectroscopic Instrument is a specialized astronomical survey that recently built the largest 3D map of the universe to study dark energy. Different schools, institutions, universities, they're all involved in this. It's something that kind of got started in the last 10-ish years, so it's more new and modern. The mysterious force, of course, they're trying to study dark energy, which is some mysterious thing that is driving cosmic acceleration. DESI's data has shocked the scientific community by suggesting that dark energy might be weakening or changing over time rather than staying perfectly constant. So things like that, I mean, I've asked people about this that are working on this, and I think they are basically saying that they need more data to really... Okay, talk to you soon. The Indian King. I took PCB and I answered. Oh. Hi, brother. Hope you're doing okay. Thank you. Busy taking Calculus 1. It's really different from pre-calc. Hello, Psycho. Hello, Justin. Hello, Noah. No, I was just saying bye to Mr. Drew. I'm still here for a few minutes. I just saw somebody do a gift. I don't know if that was real or not, but thank you so much. What did I do this summer? What do you mean? It's still summer, right? Don't tell me. I refuse to accept anything but summer until at least October. I refuse Christmas. Thank you, Stewart. Stew. Okay. All right, so let me tell you a little bit about the Lambda CDM model. So I was telling you how there are various different cosmological models. Why? Because cosmology is a field where you can do things sort of in simulation kind of way, play with parameters, see what kind of universe you get, and then you can compare to certain observations and see like what's kind of matching up the best. And sometimes, like, you know, a lot has happened more recently in this century of the 21st century where we can, you know, really measure things a lot better. We have experiments, instruments that are much, much better than before. But, you know, before that, we kind of had these theories or models and we really couldn't verify everything right away. So, so, the standard model of the universe that makes the most sense of global observations is the Lambda CDM model. So that is cold dark matter. So that is one model. Okay, so I wanted to give you like one example of a model, and there are others. It relies on 6 basic parameters to accurately describe the cosmic microwave background, the universe's oldest light, element abundances, and large-scale galaxy structures. So what is lambda CDM? So the CDM part is cold dark matter, so it's invisible, slow-moving matter that provides the gravitational scaffolding for galaxies to form. So it's a dark matter model, basically, giving certain constraints on what dark matter could be. And then what's the lambda part? This is where the cosmological constant comes in, which has to do with the dark energy side of things. So this is Einstein's original variable. So Einstein actually introduced something called the cosmological constant in his theory. And that is still relevant here and now today in terms of what it might mean for dark energy. So this treats dark energy as an immutable, unchanging property of space itself. In this model, as the universe expands, the density of dark energy remains perfectly constant. So Einstein had a cosmological constant in his equations at this point over 100 years ago. So he's a pretty ahead of his time kind of guy. And he needed to have that in his gravitation equations because he needed something to balance out gravitation in the universe. So he put something there basically to kind of say that, well, if gravitation was the only thing, then the universe could have collapsed upon itself, but it doesn't. So there has to be some other thing that kind of makes it balanced. Turns out that actually the universe is going the other way. It's not collapsing. It's not even balanced. It's actually expanding, and its expansion is accelerating. So then the way he did it was that constant, cosmological constant. So it treats dark energy, once again, as an immutable, unchanging property of space itself. A property of space itself. Where universe expands, the density of dark energy, whatever that is, remains perfectly constant. So now, let's say we're going out to measure things and see whether this theory, whether let's say this model is right or not. You can operate based on this model, but then you go out and observe, and you're basically going to constrain the model. And your measurement could be something different, and then you learn to adjust your model. Okay? So this is very common. People come up with models, they come up with theories, and then you have to test it out. You have to actually go out and see what nature has to say. And I'm not sure how ready their results are, but I do believe just kind of quickly looking it up is saying that they found some data that where they might be, instead of that lambda cosmological constant way of thinking, which is what we often, we could use, which is what we historically kind of used. It could be maybe that they're finding evidence that dark energy could be weakening or changing over time rather than staying perfectly constant. I would not be super surprised if it was not staying perfectly constant and if they found some kind of more interesting nature of it. But the fact remains that, yeah, the universe is expanding, its expansion is accelerating. Exactly what model, exactly what the parameters have to be to make that happen is evolving over time, let's just say. Not only has the universe evolved, but also our ability to track it and measure has also been evolving. Okay? It's 3 in the morning. Thank you, Ligmag. Ligmag is saying, I love your focus. I have too much focus. Everything melting while volcanoes. Hi, Yasir. How fast does... Okay. Thank you, Liberal Tears. Oh, thank you, Justin. Can I pull out a string out of my nose? Well, apparently all the things are strings, so yeah. I sure can. Aw. Good. Be a good boy. Do you live in Germany? No. I'm so lovely when I don't talk about physics? So, okay, 1 second. Okay. I'm looking up something. Don't take it bad. When you talk about physics, it's great and so professional, the doctor's side wakes up. Right? I need that side to wake up. Sometimes. Inflation versus dark energy. Let's talk about that. So somebody was mentioning something about expansion from the Big Bang, and I wanted to clarify that we have to be careful about understanding those two things. So let's talk about it. Let's see, what is this? Let me get this reference for you guys. Did you subscribe? Okay. This is the Department of Energy. I actually interviewed for a postdoc with the DOE. Which one is this? Office of Science. So this is the official energy.gov Department of Energy, who I guess we have convinced to fund all this to some extent. My hair is really curly right now, isn't it? Right here. This is dark energy right here. Oh my god. DOE. Okay. The universe. Let me give you this link. Oh my god, Mayall telescope at Kitt Peak. So by the way, this is in by the way, Berkeley Lab is one place to work for this. I gave a talk there. Actually, it was a lot of fun. I went to Alcatraz, like I went and gave a talk at Berkeley, and then I went and saw the Alcatraz Island. It was really cool. Okay. Brings back some memories. That link is my link that I shared from the Department of Energy on this topic. So, for your information. What? What are you laughing about? Oh. So in Tucson, Arizona, we have this thing called the Mayall telescope. So there's a 4-meter telescope called Mayall in Arizona at the Kitt Peak National Observatory, 56 miles southwest of Tucson. And that is what houses the very powerful Dark Energy Spectroscopic Instrument, DESI. Okay, so let me give you that as well. You know what? I'll put that in my description. Today's live is actually about dark energy to an extent because of one of the questions you guys asked. That's actually really cool. I'm just putting some information in the description here so that you can look at it. This is called DOE Explains Cosmic Acceleration and Dark Energy. Feel free to take a look. What did one of you say? This live should be called what? Cosmic Princess and Dark Energy? Yes. Good job, just in case. What is, how is the audio for this live, by the way? What is the audio like? Is it good? Oh, thank you. the audio is very clear, like crystal. The audio is perfect. We can hear you from the moon. Oh, you guys are so friendly. You're so friendly and helpful. Thank you so much, guys. Okay, so now let me tell you. I'm so excited. I love this. The universe is expanding, and it expands a little faster all the time. Scientists call the speeding up of this expansion cosmic acceleration. This growth increases the distance between points in the universe, just like stretching a rubber sheet would make points on that sheet move further and further apart. The universe has experienced two distinct periods of cosmic acceleration, not to be confused with each other. So this is why I wanted to talk about inflation versus the expansion that happens from dark energy. The first is called inflation. This occurred a fraction of a second after the Big Bang. So the expansion that comes from what people say the Big Bang, is something wrong with my connection? That expansion that comes from Big Bang or shortly after the Big Bang is called inflation. So just a fraction of a second after the Big Bang, this started. The second, the other type of cosmic acceleration is my live working? Anyway, the other type of cosmic acceleration is an extended period of cosmic acceleration that began about 9 billion years after the Big Bang. And continues today. Scientists discovered the increasing expansion of the universe in 1998. So 98 is the time when we found really strong evidence about this expansion, which is accelerating. And this was done through observations of distant supernovae, which are exploding stars. The scientists who discovered cosmic acceleration received the Nobel Prize in Physics in the year 2011. Yep. Okay. And this discovery posed a new question that scientists continue to explore today, which is, what is dark energy? Dark energy is a topic of research. We're actively trying to, find more information about this now. But whatever it is, it's overcoming the effect of gravity and pulling our universe apart. Dark energy may be an inherent feature of the universe, or it could be something related to new and unknown particles or forces. It could also be a hint that Einstein's theory of general relativity is not a complete description of gravity. But all in all, dark energy accounts for about 70% of the total mass energy of the universe. And dark matter, which is another mystery, accounts for about 25% of the universe's mass energy. with ordinary matter being just 5%. I'm reading from the link that I just shared with you guys. Well, whether there is a mistake somewhere or not, even if there's a mistake, that should also get resolved with our work, with these experiments, because if there's a mistake, it has to be caught. GR has to be challenged concretely, since general relativity, there isn't, a lot of its predictions have come true. So you have to have concrete finding that gives us something new to go with, okay? But that is to be kept in mind when we consider cosmic inflation versus dark energy expansion. Once again, cosmic inflation is something that happened within a fraction of a second after the Big Bang. And dark energy expansion it started about 9 billion years ago, apparently. Or sorry, it started about 9 billion years after the Big Bang. So 4 billion years ago. I'm just wondering, why is that number same as like the age of our solar system? If I'm reading that right. Cosmic inflation ended almost instantly. It only happened for like 10 to the minus 32 seconds, but please double check. Dark energy expansion is ongoing at this time. So, this dark energy expansion thing was not the dominant, like it was not so important earlier on. The universe has gone through changes. The universe literally has changed, and currently dark energy is very important. I would say, yeah, suspicious. I mean, I'm just thinking. This topic is a mystery, so we can challenge it. Cosmic inflation was incredibly rapid. Grew, the speed was like 10 to the 26 times, it grew to 10 to the 26 times larger. Dark energy expansion is comparatively slow. So those are some of the differences. Don't get those confused. But during inflation, space expanded faster than the speed of light, taking an object smaller than a single atom and instantly blowing it up to macroscopic scales. So oftentimes you will see that people will be trying to kind of understand what happened, the physics of that moment, and it's not easy. And but something that's obviously incredibly interesting and relevant to understanding the universe deeply. Dark energy, this is a more later stage phenomenon. It's happening right now, and we're pretty old universe at this point. So for the first several billion years, gravity successfully slowed the universe down from that initial huge inflation expansion. However, about 5 billion years ago, as matter thinned out, dark energy became dominant and began gently accelerating space apart. And the interesting thing is, like, the farther away you go, the farther away you go. It speeds up, as far as I understand. So faraway galaxies are just getting farther and farther away. wonder. Matter thinned out. I do wonder what like did gravitation kind of reach sort of a level of distribution that provokes this anti-gravitation, if you will, which is the dark energy situation. It's a mystery. I don't know. Dark energy is widely treated as a permanent baseline feature of the universe, either as the intrinsic vacuum energy of empty space or a permanent low energy dynamic field. So all in all, we need to learn a lot more about dark energy. I'll put the link from DOE in the description of this video so that you can go read it yourself. Please do your own due diligence on this topic, because remember, this is a research topic, as in it's currently unknown, currently a mystery, and people are constantly working on this. And so our understanding is also evolving, and as more and more results come out, papers get published, we should be reading those to understand where we are at the moment, okay? Hi, Matt CO. It's in physics, and it's a PhD. And with that, thank you so much, everybody. I think I gotta go. How long have I been here? I guess 2 hours. The problem is I can talk about physics for like 2 hours and not really even think I did much. This is also interesting. Funny, I love this, and I sell Lamborghinis for a living. Hello, liberal tears. I love that you love this, and continue your successful career, and do come back to these lives. We talk about these topics a lot, dark energy, dark matter, cosmology, astronomy, all of the very interesting stuff. So if you subscribe, hit the bell notification, you should be, hope to see you again. And when you hear about this multiple times, it helps. And any topic we covered today, we probably have covered also in the past in different detail. So search the topic and hopefully you find it on my channel. Thank you so much. Good night. Sleep tight and see you soon. Good night, everybody, and especially good night to YouTube, and thanks for the stream, Dree. Thank you, just in case. Get some sleep. If you sell Lamborghinis for a living, what do you drive? By the way, I am very thankful. You guys had some really good questions, and your questions helped out with this discussion, and we covered some really interesting things. So please do keep those coming. Next time I see you live, I hope that you come with more such questions, and we will bond over that. But yeah, somebody asked about the expansion stuff, so hopefully that helps. You've put me thinking about this more. Hello, Biblical 420. You're talking big brain stuff to YouTube Live. We're not very smart. I believe in you. My ex-wife was the source of the universe's dark energy. I don't believe you, multi-text max. Go say sorry to her. Matt is a bragger. Physicists love mysteries. Hi, Matt. There is Baji. Hi, Amsang. Thank you so much. Or are you guys talking about cars now? The Mustang. Well, you guys and your fancy cars should do a super chat. You're not being very helpful. Let's see. Okay, and I did